So thank you very much, Luis, for your talk.
Okay, yeah, thanks. Great to be here. I'm going to discuss a couple of, present a couple of ongoing projects concerning some ideas to explore new physics in neutrino scattering. So the first one is about neutrino nucleon elastic scattering so the neutral current process in presence of non-standard interactions. The second one is an idea. So we propose that one could search for flavor change in neutral currents using hyperon productions at the SBN detectors at Fermilab. So in this context of new physics contributions, I'm somewhat away of my comfort zone, so I apologize in advance for any stupid thing I might say in the next half an hour or any clever thing I might omit, so sorry in advance. Now, and why is this not coming? It's caught by the upper. Okay, so in general, non-standard interactions or other more general scenarios involving neutrino interactions, they can be at least potentially accessed using, well, for example, using lepton decays, tau decays. Beta decays also provide valuable information. And why not? Also other decays of other hadrons, semi-leptonic decays of B mesons, for example. We know that there are a number of also in that field, there are flavor anomalies. Also they slowly disappear, but anyway, that's another story. Of course, oscillations probe neutrino interactions through matter effects. We also heard yesterday that in principle, cosmology has some sensitivity to non-standard interactions. And coming to neutrino scattering at the detection site. So we have obviously the constraints, the ideas to constrain some of the existing anomalies. We heard about it on Monday from Georgia. There will be also another related talk this afternoon. Apart from that, so this kind of searches for non-standard interactions, the studies to constraints, the non-interaction parameters, they essentially focus on, okay, this is not working. Non so se sei stato tu o sono stato io. Okay, now it's working. Okay, so I was going to say that so this review by Farzana and Tortola is going to be my reference for the bounds, the regions of the couplings or Wilson coefficients, and they essentially come from scenarios from processes in which the input, so the processes are simple enough such that the hadronic input is as well known as possible to minimize the model dependence that you can have. So one such a case is, of course, a neutrino electron scattering, in which, except for possible backgrounds, you don't have any hadronic input. Coherent elastic neutrino nucleus scattering is another example where, in principle, what you need is ground state distributions and nothing more. Then you can also consider the scattering on quasi-free quarks in the deep inelastic regime. And our idea is to add another item to this list. Namely, we suggest to consider elastic neutrino or anti-neutrino nucleon scattering using lattice QCD input. It will be clear later why I emphasize this point. Now, unfortunately, the present scenario with data for this process is not very promising. So we have only the bubble chamber data from the 80s, particularly these measurements made at Brookhaven, where, well, we know that bubble chamber data, they have low statistics. The fluxes were not well understood, but I'm convinced that for the oscillation program, for the precision era, we need new information about neutrino cross sections on elementary targets, on hydrogen and deuterium. And there are some ideas in the market about how one could remeasure those cross sections, either directly with a modern bubble chamber, preferably one that is not going to explode, or indirectly using hydrogen-enriched targets and kinematic subtraction techniques. So I'm optimistic that this kind of measurements will come sooner than later. Now, on the side of lattice QCD, those of you that were at Neutrino might remember I expressed caution about declaring the present status of these lattice results as the state of the art. But on the other hand, I'm still optimistic that we will have really, I mean, people doing these simulations and analyzing the results, they will have reliable input for form factors coming from QCD, from first principles, and controlling the systematic uncertainties. Okay, so here is the idea of this calculation. So we have the standard non-standard interaction Lagrangian, which I'm sure most of you know very well. In principle, one could add other kinds of interactions here, other types of Lorentz constructions, but in this case, we have considered only vector and axial vector ones. And to make this study, it was convenient to combine both the standard model and the non-standard interactions within a single effective Lagrangian. We are in the limit in which the propagator, the C-boson propagator can be treated as static. So we have essentially a coupling times a lepton current, which is not necessarily diagonal in the neutrino flavor, contracted with a hadron current that now encompasses the diagonal in flavor standard model current and the non-standard interaction one. And for this current, so this current, we now take the nucleon matrix element of this current. And as in the standard model case, it is well known that we can parameterize this matrix element in terms of 4 form factors, 2 vector and 2 axials. In the case of neutral current, the pseudo-scalar form factor doesn't contribute because we have massless leptons, so I'm not writing it explicitly. And then if we do the math, we get these form factors, right? These 3 form factors in terms of the Wilson coefficients. I have dropped now for simplicity the lepton flavor indices, and so we have electromagnetic form factors of protons and neutrons that in principle we can extract from experiment, from electron scattering experiment. We were going to assume that they are precisely known. We have also strange form factors, vector and axial. And then also in the axial current, we now have the isobector combination, so U minus D, which is the same one we have in the standard model, that in principle we can probe in experimentally. But we also have an isoscalar combination. So U plus D, which is not probed with standard model with weak interactions. And this combination, you can see that it essentially, it is degenerate with the contribution from the strangeness content of the nucleon spin. So both of them are isospin singlet. So this is the reason why I emphasize that to do this kind of studies, it is desirable to have lattice QCD input, even if we assume the scenario in which, okay, charge current interactions don't involve any new physics, so we get all the form factors, we measure all the form factors there, and use isospin symmetry to relate them to the neutral current case. Even in that case, we would not be able to identify the isoscalar form factor. It is not probed in charge current interactions. So we would not be able to separate these two contributions. Right, but well, in principle, in the lattice, it is possible to perform a flavor decomposition of the current. And actually this has been done in these two papers, at least by one of the lattice collaborations, specifically the extended twisted mass collaboration has done this kind of studies, and we have used their parametrizations to make some estimates. Now, regarding the couplings, so we are going to assume that the non-standard interaction couplings are real. Flavor diagonal, we are only going to consider this case. We neglect, actually, it was in these expressions, I was already neglecting strange Wilson coefficients, because simply they would be a small modification of the already small strange form factors of the nucleon, so I'm neglecting them. And then the confidence level intervals for the remaining 4 Wilson coefficients, we are taking from this paper, and they are extracted using a combination of atmospheric oscillations at super K and high energy scattering at nu-def. So here you can see, for example, they have the kind of bands that we get for neutrino and anti-neutrino scattering. This is isolated nucleons that we don't have, but anyway, just for completeness, we are showing, and the same one here for protons. We are not showing the band for coming from the lattice result, which is much smaller. Perhaps we should, but I don't want to give the impression that this is the ultimate result. I think to be confident, we still need new complementary determinations of this flavor decomposed contributions of the axial current from different lattice collaborations. We are neglecting correlations among the Wilson coefficients, although if you look at these plots, they don't really look negligible. The thing is that Marian Tortola tells me that the correlation matrices are lost. So actually, a good idea that we are discussing is that one could revisit these feeds, including, again, as it was done originally, super K and nu-def data, but perhaps adding, even if we consider the old BNL data and the current lattice QCD input, this might be interesting. And of course, if there are new data, even better. So my hope is that this, in such a joint feed, one could break some of the degeneracies that the feeds find. Another source of potential source of information about about non-standard interactions in this case could come from the polarization of the outgoing nucleon, because in weak interactions, the hadrons that you produce are polarized. So to explore this, we have followed the formalism that was set by Bilienki, which I find particularly nice compared to others that you find in the literature. It's fully covariant, and you can write the polarization form vector as the average of the spin, and it at some point you end up with the ratio involving the spin density matrix, which is given by this expression here. So we have ratios. Contraction in the denominator, we have a contraction of the lepton tensor with essentially the hadron tensor. So in the denominator, we have cross sections. In the numerator, we have some asymmetry, some spin asymmetries. And of course, all the information about the nucleon structure and the non-standard interactions are all encoded in these gammas that appear in the numerator and in the denominator. So this is an illustration of the kind of dependencies that we obtain. So this is for a fixed neutrino energy, 1 GeV, as a function of q squared. This is the longitudinal polarization. So here the polarization vectors are given in the rest frame of the nucleon, of the final nucleon. So the longitudinal polarization is in the direction of the momentum. The transverse polarization is perpendicular to this vector, but in the scattering plane. So we have both of them here. In the case of real Wilson coefficients, you only have polarization vectors in the scattering plane. In order to get a contribution perpendicular to the plane, we need complex Wilson coefficients. I mean, unfortunately, in the case of neutral current interactions I'm considering here, you would not be able to. You don't identify the scattering plane, so you would not be able to distinguish, to separate the different contributions. But still, you can see how how the bands look like. You don't be deceived by the scale, the size of the bands in both the longitudinal and the transverse cases. They are similar. It is just that as q squared increases and the energy of the nucleon increases, increases not high, not in the way Carlos defined in the previous talk. So this is hundreds of MeV energies these nucleons will have, but in this case, at the limit of high q squared, in the case of neutrinos, the longitudinal polarization of the nucleon goes to 1. For neutrinos, in the case of antineutrinos, it goes to -1. In the case of antineutrinos, goes to 1. This is as expected, and the transverse component goes to 0. Of course, to study this experimentally, one would need sort of magnetic field which would change the trajectories of these nucleons. I don't know if this is feasible. An alternative that is actually being discussed nowadays is whether one could have polarized targets. In this case, one would see some asymmetries in the angular distributions of the final particles. That would be something nice to consider. We haven't done it so far. Another very closely related process in which you can be more sensitive to the polarization of the final baryon, and which actually helps me to bridge to the second project, is polarization. So is the production of hyperons induced by antineutrinos. So charge current interactions are not diagonal in the quark flavor, which means that with antineutrinos, but not with neutrinos, it is possible to change U quarks into S quarks at the price of having a smaller mixing matrix element. This means that we can have quasi-elastic processes in which antineutrinos interact with protons and neutrons, leading to hyperons in the final state. And these hyperons, in the same way as the protons discussed previously, these hyperons are polarized. And the advantage in this case would be that this polarization can be directly inferred from the asymmetries in the decay products. The nucleon and the pion, into which, for example, the lambda decays will exhibit an asymmetry in the lambda rest frame, which depends on the lambda polarization. This coefficient alpha is known, is measured. Of course, to study this kind of cross-section and specifically the polarization, we would need, again, some experiment on protons. We don't have this, but what we do have right now, what is a reality, is the first measurement of lambda production on argon, on liquid argon with anti-neutrinos. That was published last year by Microboom. So far, they have only, so they reported only 5 events above the background, but this is only small fraction of the collected data, though they have 4 times more events to come. Now, if you study now this process, what you see is that in the conditions, in the energy regime of Microboom, apart from the quasi-elastic scattering I just mentioned before, hyperons could be produced together with pions, right? And they would, in principle, contribute to the Microboom measurements in this, in this extra X here that could have any known strange particle. In addition to that, as this is taking place in on argon, so hyperons feel a mean field potential, and they also experience inelastic collisions on their way out of the nucleus. So this also has to be taken into account. If you do that, what you see is that these collisions, these final state interactions, they slow down the hyperons, which are accumulate at low kinetic energies. And you also see that there is some enhancement in the productions of specifically lambdas because of sigma to lambda conversion in final state interactions. And then the inelastic channel, the lambda pi channel, contributes again with the flux used by Microboom, contributes some 15%. However, the experiment has detection thresholds for the lambda decay products. Specifically, the threshold for pion momentum is 300 MeV, and for pion momentum is 100 MeV. And this leads to phase space restrictions that are going to affect, namely, the part where you see the enhancement. Indeed, what happens when you take into account these phase space restrictions is that the number of observed or potentially observed hyperon is strongly reduced. So look at the scale. This is a 60 here. This is a 16 here. Simply the detector becomes blind to the region of to hyperons with energies below 30, 40 MeVs of kinetic energy. In turn, the impact in the remaining signal, the impact of final state interactions is smaller, so it reduces the model dependence of the result. And the contribution from the inelastic scattering naturally increases. So now, with the actual thresholds of the measurement, 1 of every 3 events measured at Microboom comes from inelastic scattering. So comparing to the cross-section value provided by Microboom is pretty much useless because it's only 5 events, so the error bars are huge. But again, as I said, they have more data, and SBND is probably going to have a lot more data. So we actually predict that in the using the SBND flux, assuming 10 to 13 times 10 to the 20 POTs in 3 years. I don't know if this is optimistic, but this is what we were told at some point. So you can see that without thresholds, more than 1,000, up to 2,000 lambda hyperons would be produced. If the thresholds are the same as in microboom, then again, the reduction is strong, but still there are a few hundreds left to be seen. If the threshold are more optimistic, as some people in microboom tell me that they expect to have proton momentum thresholds around 200 MeV and pi momentum around 50. Remember, in the case of microboom, these numbers are 300 and 100, respectively. So with these detection thresholds, we can still have around 1,000 lambdas at SBND. And here you can see that the distributions here, you can see double. So the distributions of these events in two variables, again, the hyperon kinetic energy, but also the relative angle between the hyperon and the final muon. So you can see that quasi-elastic scattering and the inelastic process have different angular distributions, which is potentially interesting, but you might be wondering what this has to do with the subject of my talk, which was new physics. Well, the point is the following. All these events that we are predicted, that we expect to see at SBND, right? All those come from the flux contaminations, because remember, we need antineutrinos. So all those are coming from the flux contamination at the measurements, because the experiment is going to be running in neutrino mode, which is this flux over here. Our idea is that then once you're going to have some good information, some ways to constrain the standard model contributions from antineutrinos, one can use the neutrino flux to search for flavor changing neutral currents. So in this case, one would be looking for D to S transitions, which are suppressed in the standard model. They are not zero, but they would only come from electroweak loops and are therefore very, very small. One can, to study this kind of transitions, one can write an effective Hamiltonian, which is very similar to the one of non-standard interactions. Now the difference is that the part that is non-diagonal in flavor is the quark contribution. So we have D to S vector and axial transitions with the corresponding Wilson coefficients. And we are, for simplicity, assuming that neutrinos are only left-handed, as in the standard model. And we are assuming that the Hamiltonian, the interaction is diagonal in flavor. We also take the coefficients real, ignoring CP violation effects. Now, it turns out that these Wilson coefficients, they can be constrained using kaon decays. In fact, there are some recent measurements at the J-Park and CERN that have allowed to constrain the vector Wilson coefficient very, very, very strongly. Essentially, using kaon to pion decay. So what they find, they find upper limits of the Wilson that already start hitting the results in the standard model, which are very, very small. However, the axial counterpart is known with much smaller precision. As you can see here, there are orders of magnitude different. It would have to come now from kaon to pion decay. So this is for some reason, I frankly speaking don't really know, but this process is much less understood. Probably it's just a matter of statistics and phase space. In addition, by the way, these bounds I am showing here assume that the flavor changing contribution is democratically distributed in all the three flavors, but if it were to be concentrated in a single flavor, then the coefficient has to be increased by a factor of square root of 3. Okay, so we have all the last point, which is nice, is that now we can, the matrix element for the flavor change in neutral current hadron transitions, they can be related to the corresponding ones for the standard model process with antineutrinos just by isospin rotations. We don't need SU3 flavor rotations, just assuming isospin symmetry, which is really good, one can relate the matrix elements that we need for these calculations with the one in the standard model process. And okay, of course, this is taking place on argon, so we need to again take into account final state interactions that again pushes the lambdas. This is specifically for lambdas, which is essentially the one that you can cleanly measure in the experiment. So it pushes the energies to the low energy region. So again, thresholds are going to be important. And then we derived some upper bounds, assuming that you saturate the bound on the axial Wilson coefficient. So this one, we essentially are neglecting the vector 1 because it's much smaller. So you can see that from quasi-elastic scattering alone, we get without thresholds, we get 35 to 45 events as an upper bound, which would reduce to 10 with microboom thresholds, and still there will be 25 to 35 with the more optimistic SBND thresholds. And this is, again, assuming democracy in the flavor contributions. If for whatever strange reason, all the flavor change in neutral current contribution is only in the muon flavor, these numbers would have to be multiplied by 3. If it is concentrated all in other flavors, of course, you would see nothing. There are other, this is essentially my last slide. There are other contributions to the signal. Again, as I mentioned before, just as in the standard model case, one can produce also pions together with the hyperons. And this is going to be now relatively more important than in the standard model case because of energies. So the flux now peaks at the higher energy. So this process, which we are now studying, is going to be important. You can also have signal, so namely flavor change in neutral current contributions to anti-kaon and anti-kaon pion productions. These are going to be more suppressed by the flux. So they have thresholds that start above the peak of the flux. And then there will be backgrounds. The most important one is that you can produce SS bar pairs with neutral currents. This is allowed in the standard model. Fortunately, it's threshold, so you have to produce two strange quarks. So its threshold is already around 1 GeV, so it's going to be suppressed by the flux. Then eventually, just that is up to our experimental colleagues to tell how relevant it would be to miss charge lepton interactions and misidentify a charge current scattering process and misidentify it as a neutral current interaction process. Finally, well, a nice thing would be to have cancellations in ratios of the flavor change in neutral current events and the charge current events. And we do see this kind of cancellations at fixed energy. What sort of spoils it somehow is that the different fluxes that peak at different energies have different shapes. So we are also now looking for kinematic variables. So we want to perform some kinematic cuts, explore kinematic cuts that would enhance these uncertainty cancellations that are desirable to reduce the model dependence. And with this, I summarize. So we are investigating the potential of neutrino nucleon elastic scattering to disclose non-standard interactions and hopefully break some degeneracies among the parameters. This requires some input from lattice QCD in the form of quark flavor decomposition of the nucleon axial form factor, and also would be desirable to have new data on hydrogen and deuterium. In this context, polarization observables, if they can be assessed with nucleons or with hyperons, would provide additional information. So we are also exploring the opportunity for the SBN detectors to look for flavor change in neutral currents using hyperon production to constrain the poorly known axial vector part of this process. And the upper limits that we obtained so far are promising, although detection thresholds because of final state interactions are going to be important. And yes, we also want to understand better how we can maximize the uncertainty cancellations to reduce model dependence. Thank you.
Thank you very much, Luis. Yeah, Sergio.
So, Luis, given that the number of events grows towards the threshold and the final state interactions move the signal toward low energy, how uncertain are the calculations of the final state interaction?
Okay. Actually, it is an interesting trade because yes, the lower these energies are, the less reliable the calculations of final state interactions are, simply because those calculations are semi-classical. If these hyperons are very slow, you don't trust the semi-classical limit anymore. Actually, I omitted this in the talk too. But these bands are there to recall that this is the region where we don't have such a good control. So yes, on one hand, you want lower thresholds to maximize the number of events. On the other hand, this is the region where you control less your calculations. So my point is, I mean, I would, if I can, I would ask for better thresholds because they would give me some experimental hints on this region that theoretically we don't understand so well. We can always try to measure, to validate somehow the models in this region using data from antineutrinos and apply this to the flavor change in neutral current case. So I don't know if this answers your question.
Well, I was thinking about, I mean, actually not the ones that you don't see below threshold, but the ones at higher threshold, at higher energies that are moved towards threshold. And
in that case,
which is finally your estimate of the number of events that you will see. Answer the interactions. The reasons the final state interaction made the actual number of events above threshold.
It is better than in this region for theoretical reasons. Yeah, the uncertainties come from the hyperon nucleon cross sections. I don't have the numbers right now. We will have some uncertainty bands in these estimates here. And again, so I think they would still be consistent. My impression from what I have seen is that they would still allow to say something about the flavor change in neutral current events. Also, partially hoping, as I said, at the cancellation between in ratios of events, because final state interactions would be pretty much the same both cases.
And let me and have a curiosity. I don't know. I mean, maybe this is of no use at all. But I mean, Super K has measurements of neutrino proton elastic scattering. I don't know if that could be of any use with atmospheric neutrinos.
Neutrino proton at Super K.
Neutrino proton elastic scattering.
I'm using, I guess, detecting. I mean, I have not seen any result from that is competitive with the proper chambers, but maybe it's my ignorance, but I would be surprised.
No, but there are analysis of that. So I'm not. It's just neutrino proton elastic scattering.
Anti-neutrino proton, you mean? I mean,
Neutrino-
if it is
I mean,
if it is quasi-elastic and it's
elastic.
on protons or elastic, so elastic on protons has to be with anti-neutrinos, right?
Well,
So I
you have both, so
sorry.
it's atmospherics. So
Yeah, fine. It is there. Frankly speaking, I have never seen any competitive determination of any plot of this cross section coming from atmospheric neutrinos that is shown together.
no, probably that was my question actually. If those
maybe it's a flux that is not so well known.
yeah, that was my question actually.
Let's look at it. Yes.
So thank you for the beautiful lecture. So I have a couple of questions. One is on this elastic scattering of neutrino or nucleons. So I do not understand which, say, form factor you use in this energy. I mean, because you discussed this lattice, but you eventually did not discuss.
So for consistency, what we did here to
yeah,
do
this
the
one.
calculation,
Yes.
we used for the vector form factors, we used the empirical parametrizations. For all the other axial ones and also the strangeness content of the no, actually here we use also the empirical, sorry. But for the axial ones, just to be consistent, we took all of them from these two lattice papers.
Yeah. So and this is included in next slide,
Yeah,
because
yes.
I do not see any bending, so it's straight.
You mean this?
Yeah.
Oh, this is the way. I mean, quasi-elastic scattering tends to saturate when you increase the energy.
Thanks, perfect. So the other question is, you studied this flavor changing. This is very interesting. I wonder whether there are valuable constraints from chem physics. I mean, there are chem factories, Daphne and all that, in particular for this last process you discussed, whether they can be compared or not in some framework.
My understanding is that probably they are aware, but my understanding is that the new results that are now the state of the art are coming from J Park and NA62. This is my understanding. Frankly speaking, I didn't do an extensive search in the literature. I relied on this paper.
Further questions or comments? No? Okay, if not, let us thank Luis again.